Hello everyone. In this video, I'm going to walk you through question 6, uh, part 2 of our ROF homework exercise. The question is related to the circular waveguide. And before going forward, I'm going to give you a little bit of background information. And I might need to add another video to go through the lectures on circular waveguide. So basically, the question, according to the question, you have a electromagnetic wave of 10 gigahertz propagating at dominant motion along an air-filled circular waveguide. And the waveguide has a radius of 1 centimeter. And we are going to calculate the cutoff frequency, the guide wavelength, the wave impedance. So before going forward, I need to tell you, with this kind of question, you will need to solve you don't need to solve the Basel function, but you need to have some knowledge of this, at least a little bit. And you also need to have a table of the roots of the Basel function, Basel equation. And I have already given this to you. And what you need to do is to look at the roots. And uh, you have two kinds of roots. One is the roots of the basic Basel function. And this one will be used for the TMO. And I'm going to enlarge this for you. So this is the Basel function, the root of the Basel function. Yeah. When you equate this to 0. Yeah, when this Basel function is like this, and when you equate this to 0, then you are going to get the value for the cosine. And uh, for the cosine, for example, when you are looking at J0, um, you will have one cosine, two cosine, three cosine, and this cosine corresponds to the table, the value here, the 0, 1. And how about the other value? The other value is here. It is about 5 point, actually not. Actually. Okay, anyway, for 0, you can substitute the value here and just focus on the table. And for each uh, one node example, you get multiple root and all the roots they can be found in the table. And you also have another table, so-called the roots of the partial derivative. This is the solutions to the equation with the derivative of partial function, and we equate this to 0. So the difference between these two tables lies in the derivative. So for this one, you get J0 of x, and for this one you get J1, and then you need to take the derivative and equate it to zero, and then you can get this rule. I'm going to enlarge it to the so you can look at it more clearly. Okay. Okay. So I've already given this information to the handout, and the next thing I'm going to do is to give you some to switch you back to the regular mode. So, stop sharing. So you are now looking at my whiteboard, and before before doing anything, I need to give you some very preliminary information. So for circular waveguide, you don't have x or y parameter, but you have a radius. So for example, this is the circular waveguide. You've got a radius here, and this radius is a. Yeah. Uh, the radius here is r, but the total radius here is equal to a. Okay, a represents the radius of the waveguide. But if you are talking about the inner radius at any point between the center and the outermost exterior of the waveguide, then we refer it to r. R. And we also have we are going to use, sorry, it's better to, so I'm going to, I used the wrong ink. Very difficult to erase the text. Okay, got it. So X and then Y. And if you refer to a particular point in the circumference of the circle, then you will end up with an angle, and this angle is the axial angle. Uh, so for the circular waveguide, the parameters that you're looking at is R and perhaps phi as well. And other than that, you don't have too many parameters. And as before, for circular waveguide, you have TM mode and TE mode. TE modes. In TE modes, the propagation, the electric field in the propagation vector uh, in the direction of propagation is zero. Uh, but the magnetic field is not zero. Magnetic field in the direction of propagation is not zero. And you might wonder how does the expression look like? I also want to know, but I will be you don't need to worry about that. Right? It's like this. I will derive it in another video, and then you will have Nm, where Nm represents the mode, and then Jn, and then Kc, where K of C is the cutoff wave number, and then the radius. Uh, with the radius is R. This means the length between the center and any points between the center and the exterior circumference of the waveguide. So, and then you will get cosine values, and then J K Z and then V. So this is the formula for the magnetic field in a hex direction. And you can also use uh, other formula to work out the electric field or magnetic field in other directions. For example, the the radial electric field. You can use this way to calculate this. And then and similarly, right, you can also find uh, the circular electric field is omega k c squared. And then this time, right, is uh, the Arnold derivative. And you can also calculate the magnetic field in the radar, in the other direction, and this will become kc squared, and then k of v, and then and similarly for the magnetic field, circular magnetic field, you can calculate this according to the formula here. Now, um, first of all, you need to know the cutoff frequency. The cutoff is very easy, right? You just substitute R equal to A here, right? The cutoff can be found by substituting R equals to A to equation 1. So if you do that, first you need to find the electric field first. You need to uh, the electric field in the direction. The electric field here is uh, the so you need to find the first tangential electric field is always 0. So E phi is the electric field like this. There are two electric field components, two tangential electric field. Uh, the first one is E of Z, and this, of course, you already know it is 0. Another is E of Y, it should be 0. The tangential, yeah, I'm talking about tangential. Uh, when R is equal to A. So you just substitute to this here. Now first you need to calculate the electric field first according to this equation kc squared, and then when you calculate this you will get uh, A N M and then J N K Z R. And do not forget that you need to calculate. And then the rest will be the same. But this one has to be zero. This means no other expression in the equation will be zero except for the partial function, the root. So you need to put, yeah, by the way, you need to put r equals to a here. So a is equals to 0. So from here, you can calculate the root. You can use the lookup table to find the root of this equation. Uh, so the root to this equation is KCNM, and then P, yeah, is P and M, and then we put the palm here to represent its derivative. And from here, you can also calculate the cutoff. The cutoff is A, very simple, right? So the cutoff is like this, yeah, because this is what you get. You put 0 and then you get it. Um, the yeah, the cutoff happens when kz is equal to 0. So k of z uh, is equal to k squared minus p m over a squared. So this this guy here is the cutoff. So from the cutoff, we can calculate the uh, propagation constant in the direction of propagation. So other than that, everything will become downhill. If you want to know uh, the KZ, you can also extract it, and then you get one minus. So the formula is exactly the same for the rectangular waveguide. So, so you have got two formula to memorize it. Now, this is the formula for TE mode. Oh, by the way, you also want to know uh, the characteristic, the intrinsic impedance. TE is equal to like this. So it's similar to the rectangular waveguide. But you might also want to know TM mode. So I'm now actually you only need to memorize the formula in the black box. But how about TMO? So for TMO, then uh, you will have different set of equations. And I'm going to pin up the right box first. So it's a little bit dirty, but it won't harm our progress. You will look it. I found a way now. It cannot be read, but it can be erased. Okay, now for TMO, of course you already know that TMO, uh, the H of Z is equal to 0. E of Z is not equal to 0. So this is the number one thing you need to uh, memorize. Now, uh, first, uh, you might wonder how the expression look like for T E of Z. Uh, and you will be very surprised. It's very simple. And then cross. So previously we have a Julian palm, but this time we have Julian the partial function. And the cutoff here, sorry, the KC, KC, sorry, you also need to clean NM is equals to uh, this time there's no palm here. This means on the table you look for uh, the root of partial function rather than the root of partial derivative, and then A. So this is the key formula. And by the way, you may wonder how the intrinsic impedance look like VTM, like this. So this is the characteristic the intrinsic impedance. Now we are ready to go back to the question. Question A. Sorry. Uh, question 6. Question 6. The frequency is given to be 10 gigahertz, and the radius of the waveguide A is equal to 0.01 meter. So from here, um, you need to know the cutoff to KC. Now, the dominant mode, I forgot to tell you, the dominant mode of regular waveguide is TE11, okay? Now we are going to substitute the value here. And then now first of all we are looking at the TE mode. So the table that you look at is this one, and then A. Then you might wonder how we can get the cutoff frequency. So 2 pi fc over velocity. This is equal to Kc. Okay. So if you do a little bit of rearrangement, and Kc then velocity, and then 2 pi. And then K of t is equal to V 2 pi palm, and then according to here, yeah. So this is all you need to do. Yeah, if I'm going to calculate the cutoff, then V times 10 to the power A 2 pi, and then here the value can be, you can go back to the table. I'm going to switch you back to the document. So now you are looking at the table again. The roots that you are looking for at this stage is this one, the root of partial derivative. And um, the one that you are looking at is this value. This value is for TG11. Yeah, TG, I've already written here. TG11. 1.84. Okay, so I'm going to stop the recording, stop the sharing. So we go back here and then we do a little bit of calculation. 1.8412 and then divided by A 0.01. So if you calculate it, calculate it, so you get 8.79 gigahertz. Okay. Now the second question, the second part of the question. So this is part A, uh, and then part B, right? The guide wavelength. The guide wavelength is exactly the same as the formula you use for rectangular waveguide. So the wavelength here is 3 times tau A, and then the frequency, according to the question, is 10 gigahertz, and then 1 minus the cutoff frequency is 8.7, and the actual frequency is 10 gigahertz. So if you do it very carefully, you will get the guide wavelength to be 0.629 meter. Okay, the impedance, the intrinsic impedance, I have to use this little space here to calculate. And it's for TE mod. That's very easy. All you need to do is to use this formula. I hope you can read it, right? Yeah, I think you can read it. And then 377, and then 1 minus 8.79, 10 squared. So if you do it very carefully, you will get the value 790, right? Ohm. So this is the answer of the question. If you have any question regarding this question, please leave your question to the comment section. Okay, thank you. Bye bye.